sort of bad about the first class, but I just found out I was going to teach this not long before that. So.
Some of your audio we weren't able to
yeah.
do you mind repeating that, or did you just start?
I did just start, but okay, yeah.
You have audio now.
Oh, okay, that was it. You know, that would explain why they didn't hear me. Okay, in any case, I was just commenting about missing the first class, but you know, I was on this extended vacation that I've never been gone away that long, and to be honest, I'm still recovering to some extent. I guess you would call it jet lag, I believe is the right word, the technical term. So right now is about the time I go to sleep. So hopefully I can stay awake. But if for any reason you see my head go down up here, could somebody just come over and tap me on? Okay, in any case, here is the deal with the class. As of this point in time, we have 12 students, and unfortunately, that's not enough for a TA, but I do have a grader, so at least that. In fact, I taught a class in the spring, in this past spring. It wasn't even a 10 class. We had 10 students. I was the grader, so at least the 12 we get a little bit of help, and it is somebody else that you can contact, which is good. The more contacts you can get, the better off we are, or anybody is. So, in any case, I just wanted to point out the grader's name is Jean, Z-H-A-N-G, Zhang, I guess, and I've included her. Wherever it is here. Yes, I've included her email address. So, if like I said last time, if you have any questions on the homework or anything, please feel free to give her or send her an email. Unfortunately, I guess graders don't really even have office hours, but you can reach her by email. And for me, definitely, email is the best way to let me know if there's some question or something. And I try to respond within a day on the email. So even on Saturdays. I got to just remember to log in, and check things. One other thing, too, regarding the homeworks, we have a homework due next week. Regarding the homework, if you want, you can bring. They're always due at the class time unless you've sent me an email and asked for an extension. They're due at this time, at the class, either the start or the end of the class. So if you want, you can hand me a hard copy, and I'll make sure the grader gets it. Especially if you've requested a late homework, if you can scan it, if you have a scanner and can send it, email it to us, that's great too. But in any case, with the homework, like I said, any questions, there is at least we have a grader. So I thought I would go through the course syllabus. No, wait, I did that last time, didn't I? We were on this tour on our vacation. I had this tour guide on one place where we were at. And the weirdest thing, the person went through this, describing where we were going. And 5 minutes later, everything she repeated identically. And I just thought something was wrong, with me. But I guess, senior moment, I guess. But anyway, so I've gone through that. I just wanted to make that point about the grader and no TA, which means no discussion, of course, unfortunately. But I guess they need more 15 or 20 students. 15, I think. So if you know 3 more that need an A, or need more units, let them know. You can probably get a grader. Okay, so unless there are any other questions, let me continue tonight. What I'd like to do is, last time we talked about linear systems, and I gotta keep checking, make sure you can see that. Anyway, last time we talked about linear systems And well, or I should really just say systems. We talked about sequences and systems, and I had some notes on that here. Yeah, there. Yeah, a whole set of notes on sequences and systems. Again, I encourage you to review that carefully because you know, there will be some questions on the midterm related to that. And in fact, if you look, and I don't have a copy of it here, but if you look at the first homework set, there's a multiple choice or true or false. You know, I give you, define a system, you tell me if it's linear, nonlinear, etc. That was from previous exams. So make sure you understand the definitions, and also study this example. That's a good example that we went through last time, showing that the system x of n squared is not shift invariant. So in a review like that, make sure you understand it. That's very useful. And then also if it's been a while since you've seen complex analysis arithmetic, this primer is pretty good. Okay, so that was where we ended up last time. Tonight, what I want to do is I want to continue going through these set of notes on LSI underscore systems underscore DFT. Basically, characterization of linear shift invariant systems and the discrete time Fourier transform. So hopefully we can get through most of these tonight. And maybe have some time to talk Z-transform a little bit. But we'll see what happens. But in any event, so we know what a linear shift invariant system is, and now what we want to do is how can we characterize linear shift invariant systems? If I give you a system, when can you determine whether it's linear shift invariant or not? And we started off with a very specific way of identifying a system or describing a system, and that is through something called a linear difference equation. And this was the example we ended up with last time, where we have an equation for the output of this system as a function of current and past values of its input, as well as past values of its output. Everything's linear, and furthermore, one point I should make, I didn't quite point it out last time, there are coefficients, the b sub m and the a sub k. Those will generally have to be specified, obviously, before you can determine the system output. But what I did want to point out is these are constants, the b's and the a's. They don't depend on time. Okay, so these are constants, which is sometimes people refer to this as constant coefficient linear difference equations. So that's pretty much whether these are going to be linear or nonlinear. That's always the case in this class. These coefficients are constant in time. So we first of all start off defining this a system through the difference equations. Then I actually showed you what we call a block diagram of this system. And the block diagram contained several different elements that we'll see in most of these systems. It contained this element here. We'll use different notation later on, but this is a unit delay. Okay, so all of these systems we're going to talk about comprise unit delays. They comprise multipliers. That's what this B naught is. Later on I'll use different notation for this, but in any event, these little triangles represent multipliers, and then last but not least, they represent they also include summation or adders. So those are the basic building blocks of most of your linear difference equations, architectures: delays, multipliers, and adders. Now later on, as we go through this, much later on, we'll find out that it turns out that no system that I know of, or anyone that you could ever see, would ever consist of a block like this, where you have 1, 2, 3, 4, 5, a bunch of inputs going into one big adding device and then one output. That no system that you would implement would ever implement it that way. Instead, what they would use is, so in other words, this type of system where you have multiple inputs and one output, I can't quite see this, and just one output. No, you would never implement this adder in that way. You would instead implement it using a network of, so I'll put a cross there, you would use a network of binary adders. Okay. So you'd have to redraw, so you would have binary adders. Let's see, it's not MIMO, it's 2 in, 1 out binary adders. And we will see later how to take this block and convert it into a block or to a diagram just using binary adders. Actually, it's pretty straightforward. You just add in pairs as you go up this thing. But we'll get to that later. But those are the basic elements of all of these filters that we'll talk about. So we mentioned that last time. And I discussed an important, and you'll get a chance to use this in the first homework set, a very important MATLAB function that, so it takes all the guesswork or all the work out of generating this difference equation. Since you'll see, we'll use this difference equation a lot, MATLAB already has a function called filter, basically filter, which will essentially do this operation for you, provided you specify the inputs and you specify these constant coefficients, the b's and the a's. You specify that, then it'll do the rest. It'll generate the output for any input. And the MATLAB filter function will only generate as many output samples as you specify for input samples. So it does require some work, but and I give you an example here with a second order system. So you'll have a lot, in fact, you'll use that in this first homework set. Give you a chance to get familiar with that. If you aren't already, you probably are, but most of you probably, pretty much everybody know MATLAB here, huh? Yeah. Yeah. So you might ask, do I know MATLAB? I do not, but I teach it anyway. You know. In any case, okay. So linear shift invariant. Now we're going to focus for now on linear shift invariant system or linear time invariant system. As we talked about last time, those have a lot of really neat properties. LSI or LTI systems. So it makes sense, how can we characterize linear shift invariant systems? Well, one way is the impulse response. We talked about that last time, an impulse response. In fact, we mentioned last time, if you can give me an impulse response, and I can generate the output of a linear shift invariant system to any input through this device, or not device, or I should just k, h of k, x of n minus k, and that's equal to y of n. Okay. So if you tell me what the impulse response is of this linear shift invariant system, and you tell me it is a linear shift invariant system, then that completely characterizes the system. I know what the output is for any input. So we talked about that last time. But there are other ways of doing this. Frequency response, we haven't talked about that yet, but we will tonight. System functions, again, we will talk maybe tonight or next time. That gets into something called the Z-transforms. And linear difference equations with the initial condition. Now that we're going to talk about right at this moment. By the way, I looked at the roster, which it's it's online, and I was very impressed. We have bachelor's, master's, BS, MS, PhD. Now, when I was in school, back in the late 70s, they used to have a saying. And the saying was, now that I was back in the time 75, just after, well, yeah, just after the Vietnam War, during that time period. And I had an experience which probably many students today don't have. I couldn't find a job. I really had a hard time finding a job. I finally did. I think I did. But they had a saying. And the saying was, I've got my BS, MS, PhD, but I ain't got no JOB. Well, anyway, the jokes will get better, I promise. Anyway, so linear difference equations with initial conditions is a way of specifying or characterizing linear systems uniquely. But you got to be very, very careful. Now, as I said before, I know this is getting messy, that this difference equation obviously depends on the input, of course, depends on the b's and the a's, the coefficients, but it depends on something else. You cannot actually uniquely determine an output, given the input, for all time unless you know something else. And the something else is the initial conditions on the output. Since y of n depends on y of n minus 1, y of n minus 2, if n is 0, that means y of 0 depends on y of minus 1, y of minus 2. And so you have to kind of know what those values are before you can compute an output for every value of n. And those are called initial conditions. As it turns out, the initial conditions are very, very critical in specifying a system, and they determine everything. Initial conditions determine if the system is, as defined through this difference equation, if the system is causal, if it's linear, if it's nonlinear. So the initial conditions are absolutely critical. So that's why I said here that many different ways of characterizing linear time invariant systems, linear difference equation with initial conditions. Very, very important. So we'll discuss the importance of the linear difference equations and how that can more or less characterize these linear shift invariant systems. So let's start off with our linear difference equation with initial conditions. We'll start with one, first of all. And again, the difference equation by itself does not uniquely specify a system. Because if you don't know what the difference equation, and if you don't know what the y's are, like I just said, the example, y of 0 is a function, y of 0 is a function of y of minus 1, y of minus 2. If you don't know what those values are, then you can't determine what y of 0 is, y of 1, so that does not define a system. So you do have to specify the initial conditions. So we will talk about several. You might think, well, that's trivial. You can just set y of minus 1 equal to 0, or y of 1 equals 0, or y of minus 2 equals 0. Yes, you can do that, but you will see it makes a completely different response or behavior of the difference equation. And I can show you that with some very simple examples. And then I will go into more in depth on these simple examples. So you'll see that there's some subtleties here. But let me start out with this, a very simple example. This is a first order linear difference equation. So suppose I give you this difference equation and I ask you to determine what y is for y of n equals 0, 1, 2. Well, obviously it's going to depend on x of n for starters, so we're going to do this. We're going to let x of n equal a delta of n. So that's going to be x of n. So when we find the response with that input, that response will by definition be the impulse response, because the input is the impulse function. Okay, so now you say, okay, now I got it. Now I got it. So y of 0, if this first order difference equation, is equal to delta of 0 plus a times y of minus 1. See? Now, I presume we know what this is. This is 1. I'm going to assume we know what a is. but once again, we're stuck. We don't know what y of minus 1 is, so we can't determine the response. So let's start off with a simple example, and I'm going to give you some more information. I'm going to assume in this example that y of minus 1 is equal to 0. That's all I will tell you. Y of minus 1 is 0. Now my question is, given that I've specified this, and that's all I've specified, have I uniquely determined the output? In other words, can I compute y of n for all values of n if all I do is specify y minus 1 is 0? And the answer is yes, you can. And here's how you do it. With these initial, well, I'm not going to tell you how you do it exactly, but I will in a moment. But as it turns out, with those initial conditions, then we can determine y of n for all time. And here I've written y of n is equal to h of n by definition, since this is an impulse response, is equal to, right there, a to the n times u of n. Now, how did oh, by the way, whereas I mentioned last week, u of n is the step function. It's just 1 if n is greater than or equal to 0, and 0 if n is less than 0. So how did I actually determine that? Well, I'll show you in a few minutes. I have a complete set of notes on that. But it turns out this is for all n. For all n. So it turns out, if all I do is, if I tell you, here's my difference equation, and I've also told you y of minus 1 is 0, and I've specified x of n, done. Then you can actually determine the response for all n, and for the case where x of n is the impulse, this is the impulse response. And if you look at the impulse response, it is a h of n, for this case, is a right-sided sequence, geometric sequence. And it just goes like h, kind of, and I think you get a chance to do one of these in MATLAB. So it presumably goes like this. Well, it kind of depends on a, if a is less than 1 or if it's greater than 1. If a is greater than 1, the system won't even be stable. It'll blow up. Remember, how can we know if a system is stable or not? That's by looking at h of n. If h of n is, well, that's an aside. If h of n is absolutely summable, absolutely, in other words, the infinite sum of the absolute value of h of n converges, then the system is stable. Clearly, if a were greater than 1, in this case, this thing would blow up and h would not be absolutely summable. I didn't specify whether a is greater than or less than 1. But if it was less than 1, it's a decaying sequence. And all you needed to know was y of minus 1. Okay, and I will again come back to this in a little bit more, just fill in the blanks, if you will. What if, though, I specified what if I specified same difference equation, LDE, but I changed my initial conditions with y of plus 1 equals 0? What happens then? Well, it turns out it's the same difference equation, but it turns out that the solution for the y of n is completely different. In fact, I've worked out what the solution is. Again, I will show you how I did this in just a moment. And I find that h of n, instead of being that nice a to the n times u of n, it's all of a sudden flipped around to being left-sided. So it's not even close. Same difference equation, just all I've done is flip the initial condition around, same a, same everything. Now it's not even close to being the same response. It's now left-sided, and it looks like this. So it looks something like this. I will draw it as if it were stable. And this is h of n with that initial. This is n, and this is n equal 1. It's 0 for every value other than n equal 1 minus 2, or I'm sorry, n equals minus 1, sorry, minus 2 all the way back. In fact, what's even more interesting is, check this out. Go back to the first example where we specified y of minus 1 equals 0. Then we got that h of n is a to the n times u of n. If a is less than 1, that is a decaying exponential. So we say a is less than 1. But what happens if I specify this as my initial condition? This is my solution. Right now you have to take my word on it until we could go into a little more detail. This is my solution, h of n equal minus a to the n times u of minus n minus 1. Check this out. If a is less than 1, then, well, I'll say it's greater than 0. But if a is less than 1, then h of n goes to infinity. See? You can see it. You can see it from the formula. So you say, well, no, it doesn't. A to the n, a is less than 1, a to the n goes to 0. N is negative here. That's what this u of minus n minus 1 did. So all these values of n are negative. They're all n equal minus 1, minus 2, blah, blah, blah. And so if a is less than 1, this is a to the minus something, which is, as it gets more and more negative, it will actually blow up. So completely different solutions, and all I did was change one itty-bitty initial condition. Okay, if we assume a causal system with the above initial conditions, in other words, we assume these initial conditions, that the output of the system has initial conditions such that the output vanishes for n less than 0, then it turns out this difference equation has a unique impulse response, and thus it uniquely defines the system, and it turns out the system is linear shift invariance. Or so I thought. When I taught this, I've taught this for quite a few summers, many summers. And last summer I was teaching this, and I realized that that's not quite right about this linear shift invariance business. So I kind of went through this a lot, strained, trying to figure out my hair, no hair, but a head. I do have a head, just no hair. And I started to realize a couple of things that is in the book, especially in the text, the recommended reading text for this, the Oppenheim and Schaefer, and it's also mentioned in the Mitra book. There's kind of a little subtlety that is when you look at these difference equations. So I wrote up a whole different set, or not a whole, or I augmented my notes with some other notes, more notes, which went into a little bit more detail. And the students, it was very good, actually. Students found it to be very helpful. Unfortunately, I don't have those notes tonight. No, I do. And they're in your notes. They're already scanned in. So here were the notes that I put together. And if you will give me just a moment here, I want to do something. I have some notes that I talked about last time. Okay, good. So I put together a set of notes just last summer, which I call added notes on linear difference equations. Oh, anything there. Which I kind of fill in the blanks, and I hopefully can illuminate some of these things that I've been alluding to but didn't explain yet. Okay, so let's start off. We'll start back from the beginning, and then I'll give you some details to fill in some of the blanks. And I'll go through really 3 examples. First 2 you've pretty much already seen, but I'll just fill in the detail, and then there will be a 3rd example. And then from those examples, I can kind of explain, I think, what is going on, or what was bothering me last summer when I was going through this. So again, we'll start off with the difference equation, okay? And this is the general form. Now, if where everything is like I just described, if I divide this equation by A naught, see, MATLAB for this filter function lets you have A naught, not 1, it could be anything. But let me normalize this equation and divide everything through by A naught, and I end up with this. So you can either assume that A naught, to get to this form, you can either assume A naught is 1, or you just assume that you have coefficients A sub k and B sub k with a little hat to denote that they've been normalized by A naught, where A naught is the coefficient of y of n when y of n minus k when k is equal to 0. So anyway, this is, however you do it, you get back at this difference equation, which is what we've been using. It looks like this. And I'm just going to remove the hats, and just like I did before in the notes, in the previous notes. And as I've said, or indicated, that this equation, this difference equation, in and of itself does not uniquely determine the output, y of n. And you need these initial conditions. So let me go back through these examples, and like I said, I'll fill in the detail to show you how I got this. So let me first, again, look at the first order linear difference equation, and I will assume that we have the 0 causal initial condition. So here's my difference equation. In fact, here's the whole deal. Okay, there's my difference equation, there's my input sequence, the delta function, and here is my initial condition. So I want to determine what the impulse response of this is. And so here are the actual details. If you let y of n equal, well, no, that's by definition, y of n, h of n are going to be the same. So that's going, and they're going to be the impulse response of the difference equation. We can solve the recursion directly for n greater, let's look at first for n greater than or equal to 0. So what do you have? You have, as I've indicated here, h of 0 is equal to delta of 0 plus a times y of minus 1, or what I'm calling h of minus 1. No problem. That's 0. By definition, that's my initial condition. And this is equal to 1. Okay? Now, once we have h of 0, then we can get what h of 1 is just by solving the recursion. Now, later in the class, you will see this is not the way you get these impulse responses. There are much slicker ways with transform techniques. But for illustration, so h of 1 is going to equal, if you notice, h of 1, or y of 1, from this recursion, h of 1, which I'm calling y of 1, is going to equal to delta of 1 plus a times y of 0, see? And delta of 1, guess what? That's 0. Y of 0, well, we just worked y of 0 out, which I called h of 0. That's 1. So you get a, see? You get a. So this you get h of 1, you get a, equal a, right. And you can do the same. Once you have h of 1 or y of 1, then you can do the same trick again with y of 2. Notice that for n equal to 1, 2, 3, 4, this input is 0. Okay, so it makes life very simple for you. You just have, for those values of n, you have y of n is equal to a times y of n minus 1, or h of n is equal to a times h of n minus 1. So it's very simple. Once you have the previous value of h, you can get the next value. And when you do all that and put it together, obviously you end up with h of n is equal to a to the n times, well, I'll just leave it at a of n for n greater than or equal to 0. See? So that's how you do it. How did I do it for, how did I know, though? See, I said something stronger than this. I said that this was the solution for all n. So we have to look at n less than 0. Okay? So we've looked at it for n greater than or equal to 0. Let's take a look for n less than 0. For n, so we'll start with for n less than minus 1. What we're going to do is we're going to rewrite the difference equation. We're going to rewrite it as y of n minus 1 is equal to, you should verify this, minus x of n divided by a. See? I can do that. I mean, all I've done is I've taken x to the other side, and I've normalized it. So for n less than 0, I'm kind of using a what we would call a backward recursion. Backward recursion. Okay? Which is a good way to solve these difference equations. Now, I started with n equals minus 1. Okay, start at n, start at n equals minus 2, sorry. We want to determine what h of minus 2, wait a minute. Minus 2, n equal minus 1. Yeah, okay. Oh, I'm sorry. We'll start at n equal minus 1. And when we do that, what we discover is that if we plug it in, we find that y equal h, just use them interchangeably, that h of n minus 1, that's minus 2, right, is equal to h of minus 1, well, that already we know. We've specified that to be 0 minus x of minus 1 divided by a. But this is also 0. So h of minus 2 has to be 0, see? All follows from the fact that we pinned, or we've specified that h of minus 1 equals 0. That was our initial condition. So when you do that, you'll find that, lo and behold, h of minus 2 is 0. See, x doesn't even enter in here. X, delta of minus anything is 0. So you'll find h of minus 2 is 0, h of minus 3 is 0, and et cetera, et cetera. So when you put it all together, you end up with the solution for all n equals a to the n times u of n. Perfect. Done. Okay. So so by using that trick, the backward recursion, we can solve this thing for any value of n. And honestly, we can do the same thing. We could do the same thing for the second example. Same difference equation. Again, I'll just repeat it here. I can read it a little bit easier. Y of n equals x of n. You get sick of this simple difference equation. Minus 1, where x again is the delta function. But here, what we're going to do is we're going to specify our initial condition to be with y of plus 1 equals 0. And as I've alluded to, that changes everything. Now let's see more. Let's see what the detail is. Okay. All right. Well, we'll start for n greater than or equal to 2, and we have that h of 2 is equal to delta of 2 plus a times h of 1. And why am I starting at n greater? See what I'm doing? I'm always starting ahead of the initial condition. See, I'm always starting ahead of the initial condition. Because if I start ahead of the initial condition, then I will end up with the recursion. You can see in this case, h of 2 is equal to delta of 2. We know what that is. Plus a times h of 1. Well, we've specified that to be 0. We set that to 0. So guess what we're going to find out? That h of 2 is going to be 0. Okay, h of 1 we know is 0 by definition, by the initial condition. And if h of 2 is 0, then it's pretty simple. H of 3 is going to be 0. Everything's going to be 0. So just changing that initial condition changed the whole structure of the solution. And we can solve it that way. For n less than 1, we will use the backward recursion. Okay, backward recursion. And we namely just rewriting the difference equation. And we end up with this set of equations. And for this case, we find, lo and behold, that well, we find that h of 0 is 0 by, and you can see what I wrote down there. It's h of 1 minus delta 1, and we know those are both 0. But we're finally getting something non-zero when we consider h of minus 1. Okay? For h of minus 1, we find that that's equal to, using the backward recursion, that's h of 0, which we just showed was 0, minus delta of 0. Ah, that is 1. So now we find a non-zero value, namely h of minus 1 is minus 1 over a, and then if you keep going backwards, x of n will be 0, and you will find that, lo and behold, h of n is, when you put it together, you can see from that recursion, is equal to what I wrote before, minus a to the n times u of minus n minus 1. So that is my second example with more of the details put in. So again, it's a totally different solution. But regardless of that, notice just by adding that one initial condition, either in example 2, y of 1 is equal to 0, or y of minus 1 is equal to 0. Either one, you do get a unique solution. You can uniquely specify the system. Now, is the system linear shift invariant? We'll come back to that. We'll come.
Is it not e to the power of minus n?
What?
Is it not e to the power of minus n?
You mean here?
Yeah, minus a to the power of minus n.
Oh, I see. You're asking minus a to the n?
Minus n.
Minus n minus, that's what I have. You're wondering if that's minus n. Well, no, as it turns out, it isn't. If you look at the solution, see, this is the n value. You find that h of minus 1 is minus 1 over a. H of minus 2 is minus 1 over a squared. So, but here, the trick is n is negative, see? So the positive n values are 0 because of the u of minus n minus 1. So the only values of n here for which this is non-zero is n less than 0. So yeah, that's what makes it. So that you could write this as a to the minus the absolute value of n, for instance. So it's the index range on the n. So that is correct. It is correct as written. So those are two examples, and again, they both uniquely specify a system. Let's go a little bit further. Now the question will be, is it a linear shift-invariant system? And I'll have some words to say about that in a few minutes. But before that, I want to consider yet a third example. Okay? The third example is same difference equation. Same difference equation. I love this difference equation. Then you will say, then why don't you give us the midterm exam, just that difference equation. But we'll learn better ways to solve this stuff. You don't have to, in other words, this idea of manually going through and solving, doing the recursions, we can get away from that later on. But for right now, same difference equation, but now I'm going to change things up a little bit. First of all, I'm going to make x of n equal some constant times delta of n. Not much of a change, but I'm doing that so we can get an idea if this system is linear, not linear, etc. And then the second way I'm going to mess things up is I'm going to specify minus y of minus 1 as my initial, but I'm going to set it equal to a constant, which is not 0. So let's see what this does to our difference equation, or at least to our system solution. Well, the good news here is that in doing this, this uniquely defines a system. That's certainly true. With input k times delta of n, and with output y of n, this uniquely defines this. We can uniquely determine what y of n is. So that's good. But let's see what this system would look like with that impulse response, or what the impulse response of this system would look like. And this is sort of what happens using the same approach as I mentioned before. Since I'm specifying y of minus 1, then I will start the recursions off by looking at n. First of all, n greater than or equal to 0 first. Okay? We'll look at that just like we did before. But now you will find something a little bit different. When you go to compute y of 0, before we found it equal to 1. But now, no, it's not going to equal 1, and that was because y of minus 1 was 0. Okay? Well, now there's two differences. One is it's not 1, it's k, all right, y of 0. And the other difference is y of minus 1 is not 0. And in fact, the solution for y of 0 is k plus a times c, where again, I'm assuming c is non-zero and a is your coefficient. which I'm also assuming is non-zero. Y of 1, what does that look like? Well, y of 1 now is just a times y of 0, so you can simply compute that. And when you do, you find that that's equal to a squared times k plus a squared times c. Okay, this non-zero additive term messes, well, it changes the picture in terms of characterization of the system. And that's for n greater than or equal to 0. And then second, you will look at n less than, really n less than minus 1. We already know what things are at minus 1. That's just c. So you can solve that one too, and you end up with this solution. Before we found it was 0. Now it's no longer 0. Now, in fact, it's equal, y of n is equal to c times a to the n. Again, for n less than 0, c. Okay. Or I've done it with y of minus 2 is what I get, c over a, y of minus 3. Maybe this is, anyway, it goes as inverse powers of a. But it's not 0, and that's the point. Putting this together, which I did here, I worked because it's a very simple recursion, and going through this with the, what do I call it, the backward recursion in this case for n less than 0 and the regular recursion, I finally was able, I put it all together and I got the solution for all n. For all n. A to the n, yeah, I've written it here, but I can't read it too well, so I can, times k times u of n plus a to the, actually n plus 1 times the constant c. So you look at that for a couple of minutes and compare it with what we had before. And what we had before was basically this. Before, I will, just so you know it's a little different, we found that we would have found with this k value is equal to a to the n times k times u of n. And that was when y of minus 1 is equal to 0. Okay? So this non-zero initial condition, y of minus 1 equals c, introduces this constant, which is time dependent. It depends on n. And in fact, it'll grow or decrease with n, as does this term, depending on whether, but the point is, this is for all values of n. Okay? All values of n. This term here, the one we had before, is really 0 for n less than 0. But this is for all the values of n. Note that even when k equals 0, which is so the first case we did before was with c equal to 0, k equal to 1. But there's another case that we can look at. What about the case where k is 0? There's no input whatsoever, and the output would be this term, see? So y of n, even if k is 0, even if the input is shut off, you're still getting some output. Thus, this linear difference equation, and we can't have that. For instance, if it were a causal system, then we would find that when the input's 0, the output's got to be 0. But this is not the case. So here we've come up with a unique system, but the system is non-zero even if the input is 0. So this difference equation plus this initial condition, it does define a system, but it's not a system like what we saw in the first two examples. Another point, by the way, I should point out. Note also that if x of n is 2 times k delta of n, in other words, if we replace k with 2 times k, what is the solution? Well, the solution will be this with k replaced by 2k. So, as a little aside here, I can point out again, y of n, for this example, 3, y of n we showed was equal to a to the n times k times u of n plus a to the n plus 1. And that will be equal to t, the system response to the input k times delta of n. Okay, that's the impulse, or that's the system response to that, to k times delta of n. But what if I said, okay, But suppose my input, now suppose that x of n is equal to 2 times k. I'll just replace k with 2 times k. Then what will the output be? Well, that's pretty simple. I mean, we don't have to go back and resolve everything. It's just going to be a to the n times 2k times u of n plus a to the n plus 1 times c. Well, so what? Well, this is equal to t of 2 times k times delta of n. Now, my question to you is, what do you think? What do you think about that? Do you think that if you just, Oh, you did, I'm sorry. If you just looked at that, would you say, gee, I wonder if this system, it's a system, could it be a linear system, for example? Would you wonder that? Well, if you look at this equations for y of n under k and under 2k, you'll find, you know what? If this were gone, if this c were 0, really 0, then yeah, the output response would be linear. But with that damn c in there, that additive term, you can see no, if I replace k with 2k, this is a different solution than this up here because of this additive term. So this does not equal t of k times delta of n, and this is not a linear system. It is a system. I mean, it uniquely defines an output with that initial condition, but it's not a linear system. Non-linear system. And certainly not a linear time invariant system. So that is example 3, a difference that, right here, let me put that over here. That just shows you what difference the initial conditions can make. And that's what I say up here. The y of n equal t of 2k does not equal the response to k of delta, or I should say it's not equal to, I'm sorry, I messed that up. I got too excited there. This does not equal 2 times. Remember, that's the definition of linearity. If t of 2 times x is equal to 2 times t of x, then the system, that's a measure of linearity. It's a little bit more than that, but that's one measure. Well, clearly this isn't happening here, so the system is certainly not linear. We know that. Okay, so which is what I said here. Thus, the system is nonlinear. Okay, because of that. It is a system, but it's not linear time invariant. By the way, this is a kind of a little aside I'll let you think about. If the output of a system, y of n, is non-zero with 0 input, the system must be nonlinear by definition. I'll let you mull that over a bit. That's why I had that question mark. Why? Why would that be true? So give that some thought. And if you figure it out, let me know. Well, no. Anyway, finally, for this example, we see that the system cannot be time invariant. Here's another one. Suppose x of n is k of delta of n minus n naught. This is really a subtlety. Suppose x of n is equal to k times n minus n naught, and I will let n naught in this case be greater than 0. So you remember the deal. If the system is linear time invariant and y of n is equal to, remember this, is equal to t of x of n, then y of n minus n naught will be the response to t of x of n minus n naught, right? This is the definition of a time invariant system that has that property. So let's check this system out with that non-zero initial condition. For this example, we see that the system cannot be time invariant. Okay, so let's suppose that x of n is k times delta of n minus n naught. I think you'll see what happens. It's once again that constant a to the n plus 1 times z, resulting from the non-zero initial condition that messes everything up. So I went through that example for n less than n naught and for n greater than or equal to n naught, so that covered everything. And what I find for this case was that, and you can go through all the steps that I did, but the bottom line is that y of n, when you put it for all n, is equal to a to the n minus n naught k times u of n minus n naught. So far so good. I like that. This is just shift invariant, or it's just a shift, and so that's starting to look like this up here. So I like this part, but there's a second term. Now that's all there would be if c was 0. But here comes this term in, and it's once again this times c. So once again, this messes everything up. This is, if this were a to the n minus n naught plus 1 times this constant c, then it would be fine. But it's not. And you can, and don't take my word, you can go through go through that example or through the calculations that I did. Actually, that is taking my word, I guess, except that it isn't, because you can verify this for yourself. And you will find clearly y of n is not a shift invariant version, and due to the additive term, once again, the system defined by this with that initial condition cannot be shift invariant. So when you make like I said, everything depends on the initial conditions. Before I go further with that, let me give you an aside that I hadn't pointed out. For a given, let's just a general property of these difference equations, or at least this is how you solve these difference equations. For a given input sequence, x of n, okay? Now I've restricted myself to a first order difference equation, but I'll show you how to solve this whole thing for a general nth order difference equation. Okay, so for a given input sequence, the general linear difference equation, equation 2, which was, you recall, that was our friend, this guy, okay? That was equation 2. For a given input sequence, the general linear difference equation can be solved uniquely for n greater than or equal to 0, provided we specify y of minus 1 minus y of minus 2, y of minus n, okay? And the way you see that is, suppose we set all those values to 0, okay? So what would you find? Suppose y of minus 1, y of minus, everything is 0. What you would find is that, for that case, y of 0 is, remember, in that recursion you have two terms, which I call last time the feed forward and the feed back, okay? So if you study this is the recursion we're trying to solve. And if you study it for a minute, you'll realize that y of n, and if n were 0, is summation m equals 0 to n b sub m times x of n minus m. Okay, x of n is specified, minus summation a sub k, n is 0, y of minus k from k equal 1 to n. Now, with those initial conditions, those n initial conditions, these terms would be 0. So you would just end up with this term for y of 0. It's not 0. It depends on the input, but it only depends on the input. It does not depend on, well, I guess in a sense it does. But anyway, it only depends on the input. All the other terms from the output are 0 with those initial conditions. And similarly, y of 1, what's that equal to? That's equal to this minus, now you pick up one pass value of the output, minus a sub 1 times y of 0, where y of 0 is that, and then so on and so forth. So you can see going forward, y of 0, y of 1, y of 2, etc., all the way out, you can uniquely determine what y is with those initial conditions. For n less than minus n, now notice once again, I started n less than minus n. And you may ask, what about y of minus 1, y of minus 2, all the way up to y of minus n? Well, we don't have to worry about those. We know those are zeros. So all I need to finish this is to specify y of n for n less than minus n. And to do that, you once again use the backward recursion. So this, I write the recursion in this form. I solve the backward, or I use it in the backward form. And again, with these 0 initial conditions, I find, lo and behold, that, where is it here, that x of minus 1 minus big N is equal to this, equals to this. Again, it's just, for this case, it's just a function of the input sequence because the values of the y are 0 by the initial conditions. Y of minus 2 is equal to this, which is uniquely determined, y of minus 3. So everything is uniquely determined with those initial conditions. But notice you need all n of those initial conditions, y of minus 1 up to y of minus n. The reason why you need all n of those, because this is an nth order difference equation, linear difference equation. If it were a first order difference equation, capital N would be 1, and you'd only need that y of minus 1 or y of plus 1. So that's why those simple examples we could get by with just specifying minus 1 or y plus 1. But for the general case, you would need n initial conditions for this nth order difference equation. So anyway, oh yes, right. So in any case, that's how you would solve the difference equation. Now let me go back to discussing the difference equations. Or the initial conditions. These initial conditions, y of minus 1 equals y of minus 2, blah, 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 equals 0, do not necessarily, now this is where we're getting into the linear shift invariance, these do not necessarily guarantee that the linear difference equation corresponds to a linear time invariant system. So what I've kind of indicated in those three examples, that I went through, the first two examples had 0 initial conditions, and if you work through those examples, you would find that the systems as defined are a linear time invariant. The third example was a non-zero initial condition, and that isn't linear time invariant. So as long as we stick with 0 initial conditions, we have a good shot that the system will be linear time invariant. But as I said here, and this is what got me thinking last time I taught this, and I started to get really confused. And I thought, well, hell, that's not good. If I'm confused, then, I'm supposed to be teaching. And I didn't want to go to class saying, I don't understand this. Can somebody fill in the details? So in any case, there is a subtlety. Okay, so these initial conditions, these initial 0 initial conditions, do not necessarily guarantee that the linear difference equation corresponds to a linear shift invariant system, even though in the previous examples everything was fine. Okay, so this was the example that I came up with that really bothered me. And we can go back to example 1, which was the difference equation, the first order difference equation with y of minus 1 equals 0. We found that for this example, the response to a unit impulse response was h of n equal a to the n times u of n. Okay? So that was that very first example we looked at. Now, however, so for that case, which I didn't point out, okay, so for example 1, what we basically found was that y of n is equal to a to the n times u of n, which is equal to t, was equal to t times delta of n, which I also noted is, by definition, the impulse response, h of n. Okay? So just looking at this, you can, and what if I changed delta of n to k times delta of n? I would have gotten k times a to the n. So you say, hey, that sort of looks like it could be causal. It could be, linear time invariant. What's the other thing? Oh, causality. Also, as an aside, it looks like it's a causal system. because if that's h of n, remember what we showed for causal systems, a linear time invariant system is causal provided h of n is 0 for n less than 0. So this looks kind of like it could be linear time invariant and causal to boot, and stable if a is less than 1, or if the magnitude of a is less than 1. So that is the example that was as far as I went. But then here's what happened. Then I started to look at, well, wait a minute, shift invariance. Before I'm done with all this, let me substitute in delta of n minus n naught. Let's make sure that had better be question mark y of n minus n naught, right? Well, the first time I looked at it, and this is not what bothered me, but you'll see what it did in a second. I assumed that n naught were positive, so we're doing a positive shift backwards in time. If n naught is greater than 0, and I will say x of n is delta of n minus n naught, so it's a delayed impulse response, n naught is greater than 0, positive delay, then we know that y of n is equal to y of n is indeed equal to h of n minus n naught, is equal to a to the n minus n naught times u of n minus n naught. And by the way, you say, well, how did I write that out? You know, by inspection? What did I? No, what I did, I snuck around and I used, I used example 3. On example 3, remember we were showing it too was not shift invariant. But the beauty of it is I calculated what the response would be to this first order difference equation under these conditions, and I found somewhere that let's see. Oh yeah, there I guess. This was the response for all n, and this is the same case we're considering now, except c is 0. So. Okay, so as long as n naught is greater than 0, there is no problem. If n naught is greater than 0, then we know that y of n is equal to a to the n minus n naught times u of n minus n naught, and everybody's happy. Okay, so this looks like it could be time invariant. See, here's what bothered me. It wasn't that case. It was the case where n naught is less than 0. See, if it is time invariant, it should be time invariant for any value of n naught, whether n naught is positive or negative. This should always hold. And this is what was bothering me. If n naught is less than 0, then y of n equals a to the n minus n naught times u of n minus n naught. No, it does not equal that, okay? I knew it didn't equal that because I'd done the recursion. And if y of minus 1, again we're specifying y of minus 1 is 0, but now we're shifting the delta function ahead to n naught samples. And it turns out that screws up this invariance thing. It's no longer equal to this. And here's the calculations. You can go through these. To see this, we once again solve our simple first order difference equation recursively. Do it recursively with y of minus 1, 0, and x. Take a simple example. Let x of n equals delta of n plus 1. Okay? So it is a delayed, well, it's not, it's a shifted ahead delta impulse response, okay? So in other words, n naught is equal to minus 1. For this very simple, just simple examples. And if you do that, you will find, what I think you will find, what I found, is that a y of 0, I found out to be 0, y of 1, 0, y of 2 is 0, which that's kind of okay. Because that would mean that's kind of what you would expect if it were shift invariant. For n, but check this out. For n less than minus 1, using the backward recursion approach, then I find this. Y of minus 2 is y of minus 1 minus delta, or I'm sorry, minus 1 over a, all the way back. Putting this together, for this case where n naught is minus 1, here's what I found out. That y of n, check this out, y of n is equal to minus a to the n plus 1 times u of minus n minus 2. The n plus 1 is good, but the minus 1 minus 2 isn't what you would expect. Clearly, this won't equal h of n. What you would expect if it were shift invariant would be that h of n you would expect to equal a to the n plus 1. Remember, n minus n naught, n plus 1 times u of n plus 1. Just replace n with n minus n naught. Question mark. That's what you would expect. But no, it isn't for n less than minus 1. That isn't what you get. Instead, what you get is this, which is not the same thing. So this system is not a linear shift invariant system. That, my friends, was troublesome, because I thought that as long as you specify 0 initial conditions, these difference equations would define a linear shift invariant system. And I found, lo and behold, it doesn't. So then I started going through books. Then I'm in deep trouble, because now I have no idea what I'm talking about. That's never good. If you teach a class, make sure. If you ever teach, make sure. So I started going through, and I don't think, as I recall, and I could be wrong. If I am, my apologies to Professor Mitra. I don't think I found this. I don't think I found the resolution to this in Mitra, but maybe I did. I can't remember. It's been a while now. It's been a year. I certainly, as I recall, I did find it in, no, maybe it wasn't here. But in any case, you know what happens in this case? To resolve this issue, we introduced the notion of 0 rest conditions. Specifically, if x of n is 0 for n less than or n naught, okay, which it was in this case. In this case, yeah, for n less than n naught, which n naught happened to be minus 1, x of n was 0 with delta of n minus n naught, and n naught equals minus 1. Yeah, for this case, clearly for n less than minus 1, x of n would be 0. This was our x of n. Then we constrain y of n to also be 0 for n less than n naught. Okay, that's the little subtlety. That's how people do. Then the general difference equation with input x of n for n less than n naught does define a linear time invariant system with the following 0 rest conditions. Not y of minus 1 equals 0, but y of n naught minus 1 equals 0. Y of n naught minus 2 equals 0. Y of n naught minus capital N equals 0. Those are the explicit, what is called the 0 rest conditions. And with those conditions, and only with those conditions, are these linear difference equations. So they define not only a system, but a linear time invariant system. So I got to tell you, then I started reading through these books, and sure enough, everybody used 0 resting conditions. So then I knew what the hell they meant. So there was a little bit more to the story than that. But anyway, please review these notes. Like I said, this is kind of a subtlety. You won't need, the good news is you won't need to know all this after this part of the course, after these notes. But if you want to know what's going on, some of the subtleties, I would encourage you to review those 3-4 pages of notes. And by the way, let's go back to example 1 above. And those are very simple examples, but there's a lot of information out of those examples. Let's go back to example 1 above. Example 1 again was, this initial. So that was this case. I know you're getting tired of seeing this, or no. Y of n is equal, but I'm rewriting it so I can show you something. Y of n minus 1 plus x of n. And for this example, I picked x of n equals delta of n, and I picked y of minus 1 is equal to 0. So now what I'm going to do is I'm going to shift. I'm going to look at x of n. Now, look at this example. Now let x of n equals delta of n minus n naught, where n naught could be plus or minus. And now we're going to require that 0 initial rest condition. condition, and it looks like this. Y of n naught minus 1 is equal to y of, well, I should have been, n naught minus 2 is equal to 0. Oops, see, is equal to 0. This is not what I had before. Before I had y of minus 1 equals to 0. But now if n naught is minus 1, that would be, instead of y of minus 1 equals 0, y of minus 2 would equal 0 for initial rest conditions, for this example, rest condition. And then you will find, lo and behold, that we can see that under this condition, namely y of minus 2 equals 0, that initial condition, the output is indeed given by y of n equal a to the n plus 1 times u of n plus 1. So under this condition, system now is time invariant. Okay, is time invariant. So in fact, the system is linear time invariant. So anyway, again, I encourage you to just take a look at these notes. This is in chapter 3 of Mitra, and maybe I was wrong. I'm sorry, Professor Mitra. I think he did talk about the zero initial rest conditions. But anyway, there are some subtleties, and like I said, as we go through the course, we won't really be coming back to this very much. But at least for right now, when we talk about systems, it's good for you to review this over. You got any questions, send me an email. Or we can meet before class, that's fine too. Okay. So, to summarize, and then we can take a break here in a minute. Well, actually, I'll talk about something else. Okay, so to summarize, for causal filters, the linear difference equation uniquely defines the system. For causal filter systems, the linear difference equation, this guy, uniquely defines the system, and system is LT or SI, provided initial rest conditions. Rest conditions are assumed, okay? Are assumed. And the initial rest conditions, again, y of n naught minus 1, y of n naught minus 2, y of n naught minus n, big N, is equal to 0, okay? Initial rest conditions. So that's pretty much, and that's a lot of everything I wanted to say about linear difference equations for now. We'll come back to some examples later on. But that is so all I wanted to get across is that this linear difference equation does define a system and defines a linear time invariant system under these initial rest conditions. And those, by the way, are what we're going to assume pretty much from here on out in the class. We will assume that, so that my difference equation will define uniquely a linear time invariant system. And as such, it's uniquely characterized by the impulse response. And like I said, there's a lot of, you don't have to do these recursions backwards, forwards. There's some simple ways of solving for these using transform techniques. Okay, maybe I can say a couple of things about the transform or about frequency responses. What is the frequency response of a system? Well, the impulse response is the response to an impulse. Frequency response is the response to a sine wave, as it turns out. And not just any sine wave, a complex sine wave, okay? So, the frequency response of a system, yes, y of n is equal to t of e to the j omega n. That is the frequency response. So it's kind of the counterpart of the impulse response, except where the input now, instead of a delta function, it's this complex sine wave. So assuming the system is, and this complex sine wave, notice phase is 0, the amplitude is 1. The only thing is the frequency. In omega, that's a variable. So let's see what the response of this system is. Assume that t is linear time invariant. Okay? And let's see what the response of this system is. And here it is, very subtly, or not subtly, but very simply, this is it. Okay? Assuming the system is linear time invariant, then I know that y of n can be written as the convolution of the impulse response with x of n minus k. I know that. I know furthermore that x of n is e to the j omega n. I put that together and I get a very, very simple result, an important result, namely that if I substitute e to the j omega n for x of n, I find that I can write the response, the frequency response, as in this form. Basically, what it says is that the response of a linear time invariant system to a complex sine wave with unit amplitude and zero phase is just the sine wave, e to the j omega n. So it's also, so if the input is sinusoidal at frequency omega for a linear time invariant system, the output is sinusoidal with frequency omega, but the amplitude is no longer 1 and the phase is no longer 1. In particular, you find this output to be, well, here, let me redo that. You don't have to rewrite it, but h of e to the j omega, which I'm calling that the amplitude, you'll see why a little bit later on, times e to the j omega n, where this expression is a complex constant. Okay? And basically, and you'll see why I wrote it as e to the j omega, because for a linear time invariant system, this constant depends on omega through the term e to the j omega. We'll use that later on. But anyway, so this is a complex constant. It only depends on omega, and this is what is called the frequency response of the system. This constant, this amplitude, tells you how the system will respond to a complex sine wave at frequency omega. It will tell you if the response is 0, if it's very large. It'll tell you a lot about the system, its frequency response. And what is h of e to the j omega? Well, that's pretty straightforward. It's just equal to this term, summation h of k e to the minus j omega k. Why is that true? It falls right in the convolution. Okay? Just substitute in e to the j omega n for x of n, and that falls right out. So it follows directly from the convolution. So that is this constant, which we call the frequency response of the system. It's just summation k h of k e to the minus j omega k. And what this is, you can interpret this, and not interpret it, it is, this turns out to define the Fourier transform of the impulse response. Okay? So, if you feed the system an impulse, you will get the impulse response out. If you feed the system a complex sine wave, then you will get, well, it'll be a complex sine wave coming out, but it will be the discrete Fourier transform. The constant out in front will just be the discrete Fourier transform of the impulse response. So that's what that constant is, and that tells you everything you need to know about the system. The impulse response does, this does too, if the system is linear time invariant. And what people do is they plot this, normally, well, you can plot the magnitude, or you can plot it in dB. I'll point that out in a sec. The complex absolute value versus frequency, okay? And that tells you a lot about the system. It tells you if the system, maybe at this particular frequency, you have a resonance, maybe you have 0 at that frequency, etc. So basically it tells you the amplitude of the response of the system to a sine wave at frequency omega n. Yeah, that's enough. That's enough for now. But why don't we take a break, and I will be back in 15 minutes. Okay, I will see you in a few minutes. So far I've fallen asleep. Yes, yeah. Yes, already. Oh, man. Let's see. Okay, the paper's up. Man, I tell you. See, where I was just couple of days ago, it's 4 in the morning, so I'm still really kind of out of it. But in any event, oh yeah, there is something I wanted to mention. Oh yeah, yeah. Just take me a second to sync up again what I was doing. There is this is a question I give on a midterm once. I'm trying to see how I framed it. Okay, so let's say x of n is equal to example here. Here was a question I give. X of n is equal to e to the j omega 1 n, okay, and y of n, this is, just a general system, it's not necessarily linear time invariant or anything, was equal to e to the j omega 1 n plus e to the 2j omega 1 n. So this was my example. And my question is, this is my, well here, this is equal to t of e to the j omega 1 n. And my question is, could t be linear time invariant? And the answer is definitely no, it couldn't be, because if it were, the answer is, question mark, no, because if it were, then because if t is LTI, then we know we can characterize it by its impulse response. Then, and we would have that y of n is equal to h of k times e to the j omega 1 n minus k, which is equal to e to the j omega 1 n times that h of e, what I defined to be h of e to the j omega 1. So in other words, there's if t is linear time invariant, there's absolutely no way, if you feed a sine wave in, that you would get anything else out but that sine wave. I mean, it could be multiplied by a complex amplitude, but it'll be the sine wave at the same frequency. So actually, that's a good way to probe systems. That's one way to probe systems, to determine if they could be linear, if the systems are linear. I talked to a student who was in the mechanical engineering who had this project involving a simulator test bed. They were trying to simulate earthquakes. And the one question was to characterize it, could the system be linear or nonlinear? One of those two. And in any case, so one way she was doing, she had a simulation model for this earthquake model, and so I said, look, just feed in a sine wave, and sure enough, she got all kinds of harmonics coming out of it. So it definitely wasn't a linear system. So the point is, if you have an unknown system, you feed a sine wave in, and you get something else like harmonics and all that, the system can't be linear time invariant. And then you ask, well, so okay, it can't be linear time invariant. Is it nonlinear? Well, it's hard to tell if it's nonlinear or time invariant. You really don't know if you're getting this sort of response out. But you know it's not linear time invariant. You definitely know that. So that is the, we'll stop there for now regarding linear difference equations for right now. So we'll go back and discuss the frequency response of these systems. So that's how I define the frequency response. And here is a couple of, oh, wait a minute, let me put that over there. Yes. So here are some properties of these frequency response of a linear time invariant system. A couple of notes. One, the h of e to the j omega, as I've defined it. Remember, the way it's defined is h of e to the j omega is the discrete Fourier transform of the impulse response, k times e to the minus j omega k. And again, that falls right out of the convolution operation. So that is the definition of h of e to the j omega, and it generally is complex. So note that it is complex, and as such, we can thus express it in, now this goes back to the notes on complex arithmetic. We can express it in polar form. So we can write h of e to the j omega as some amplitude, a, which is real, times a, in fact positive, times e to the j phi of omega. Okay, we could write it like that. We can furthermore, we can expand e to the j phi and write h in this form. H is equal to a of omega, some amplitude, which is positive, times cosine phi of omega plus j times sine phi of omega. So this is generally a frequency dependent. So this is generally a frequency dependent amplitude and phase. Amplitude and phase. That's that little cartoon, that little sketch I made earlier. So sometimes people plot the magnitude, which is what I'm calling a of e to the j omega, and they plot it like this. So this is definitely, as I've sketched it, frequency-dependent amplitude. So generally frequency-dependent amplitude and phase, and it is the Fourier transform, discrete Fourier transform. Actually, we call this the discrete-time Fourier transform. I'll discuss that a little bit more later, of the impulse response. That's the frequency response. Also, as an aside, the amplitude is frequency dependent, as is the phase. Sometimes you can have systems where the amplitude is not frequency dependent. It's constant. And we'll come back to those a little bit later. Also, a of omega can be written as the complex magnitude of h of e to the j omega. Remember, that's the square root of the real part of h squared plus this plus the imaginary part of h squared, square root of all of that, and which pops out of this form too, very simply, because the real part is a cosine, the imaginary part is a sine. Square them and you get a squared, square root, and you get a. Phi of omega is the phase response of this system. A is the amplitude response, phi is the phase response, and you can calculate that through an arctangent function. Actually, in MATLAB has a, MATLAB actually has a built-in function for doing this, and the built-in function is if you have a complex number, z, and you compute, I believe it's angle of z, that will give you phase in radians, for instance. That's a MATLAB function. I should say MATLAB so you know what I was referring to. So MATLAB has that function built in. MATLAB also, as we'll talk about a little bit later on, MATLAB also has a function which will compute a of omega automatically and the phase all into one plot. Well, they put in two plots next to each other. Provided you can specify the system, the linear time invariant system, in terms of a difference equation with coefficients a and b. I'll show you some examples of that too later on. Okay, so in any case, that is the frequency response can be written in this polar form, and then you can put the whole thing together and you find that if I write it in polar form, y of n is equal to a, the positive magnitude, times e to the j phi times e to the j omega n. So you notice that, again, the system, a general linear time invariant system, will modify the amplitude of the input constant amplitude sine wave as well as its phase, too, as a function of frequency. If the amplitude is greater than 1, we say that the system at that particular frequency has gain. If A is less than 1, we say that the system at that particular frequency is lossy. And if A is equal to 1, we say the system is lossless at that frequency. I will show you systems. I will show you systems which we call all-pass systems. All-pass systems where A of omega is equal to 1 for all omega. For all omega. Well, for all omega between minus pi and pi. Okay, that's essentially all omega because everything's periodic outside of that. But I will show you systems for which A of omega equals 1. Now, phi of omega for these systems will not be constant, but A of omega, I will show you those systems. And they're very useful in filter design. So anyway, those are some properties about the magnitude of the frequency response. A lot of times what we do is we plot the magnitude of the frequency response. We convert it to dB simply by taking 20 log, the base 10 of the magnitude. That is in decibel, dB. And typically that's how we plot A. We don't plot the magnitude of H as I indicated before. We actually plot it in dB because you can see a lot more dynamic range. For systems with a real impulse response, so if H of n is real, then A, or H of e to the j omega, is complex conjugate, is complex conjugate symmetric, okay? Which is what this note is. So it has a very, very nice property that if I know what H of e to the j omega is, I automatically know what H of e to the minus j omega. Specifically, H of e to the minus j. So the negative frequency is equal to H at the positive frequency, but complex conjugate. That's the complex conjugate symmetry. This in turn implies that, I'll leave this one for you to mull over. So if your system is real, then H has this complex conjugate symmetry. H is complex. And in turn, what that implies is that the amplitude, A, it turns out that's an even function of omega. A of omega is equal to A of minus omega. Give that some thought. And by the same token, the phase, it turns out to be an odd function of frequency. Namely, phi of omega is minus phi of minus omega. So that follows directly from the definition of H. I'll let you look at that and see if you can't convince yourself of that, of the truth of that. So far we've discussed complex sine waves. What if the input was a real sine wave? Like a cosine wave, some constant times cosine, omega n plus theta. Well, in that case, the response, it kind of depends on what the system is. In particular, let's see there, what did I do? Yes. In this case, y of n is equal to, I want to make sure I get this right. Yeah, it's equal to A of omega times cosine, right, times cosine omega n plus, is that right? Yeah, plus phi of omega. I believe that's correct. If H is real. As it turns out. Why? Well, here's why. If H is not real, if you have a real sine wave going into a complex impulse response system, then things are a little bit different. But anyway, here's the detail worked out. Here's the full detail of that calculation, so you don't have to go through all that. But basically, I just worked all the details out. For x of n equal to b times cosine omega n plus theta. And what you find is that, oh, I'm sorry, that's plus theta there. Okay, it's just generally you would like to think that the output for a real sine wave input is just a phase shift version of that real sine wave multiplied by some amplitude, and that is true provided the system is real. But here's the general solution to the system response to a real sine wave. It looks like that, and I've used the fact that the real sine wave, cosine omega n plus theta, can be written as, this is always important to keep in mind, this is one of the identities, omega n plus j theta plus complex conjugate of that, minus j omega n minus j theta. So I can always express any real sine wave as a sum of two complex sine waves. And if the system is real, or I'm sorry, if the system is linear, which we're assuming here, then I know that the response to the real is sine wave is the sum of responses to the two complex sine waves. So in any case, I end up getting this result, and I express the h of e to the j omega. Not surprisingly, it's involving h of e to the j omega, but it involves, unlike the complex sine wave case, h of e to the j omega and h of e to the minus j omega. And as long as h of e to the j omega is complex conjugate symmetric, which means h of n is real, then you can write that in the form that I kind of muffed up, but in this form here, as you might expect. If h is not real, then what I did was I wrote h in terms of its complex polar representation, and I ended up with this form for the output of the filter. So this is the case where you have a real sine wave going, or cosine wave, and you have a complex impulse response. And what you end up with is two counter-rotating complex sine waves, generally with different amplitudes and phases, or at least with different amplitudes, if h of n is complex. So if the impulse response is complex, we get complex output, even though the input is a real sine wave. So little factoids about these linear systems with sine wave inputs. If the if the impulse response is real, then yes, then you get this result for the output. So that's pretty much what I wanted to say about yeah, you get that result, which is what I was trying to write down earlier. So is there anything? Yes, one other thing to notice. Before we go on to discuss the DTFT, we observe that h of e to the j omega is periodic. I mean, that's pretty clear when I wrote it in the form of h of e to the j omega. But any of these systems, and any systems with the difference equations and constant coefficients and causal or zero initial rest conditions, it turns out h, the Fourier transform of the impulse response, the discrete Fourier transform, will depend on e to the j omega, almost by definition. Remember, h is equal to summation k, h of k for the nth time, times e to the minus j omega times k. So this is a function. It is a function of e to the j omega through all of these terms. And being so, being a function of that, then that automatically implies that, because we know that e to the j omega plus 2 pi is equal to e to the j omega. So what that means is that the exponential, the complex exponential is periodic in 2 pi, which pretty much means that the frequency response is periodic in 2 pi. And I pointed that out at the last class, where I was looking at complex sequences that were sine waves, just saying that omega in the discrete world, it's periodic, so it can't be infinitely long. It'll just start repeating, or at least the frequency response will start repeating. Typically, we plot only one period of h, or its magnitude, or its phase. For sampled data systems, omega equal pi corresponds to the highest frequency which can be sampled without aliasing. I'm just laying that out there. We'll come back to that complete discussion of sampling, which you'll be able to see where that sentence comes from. But I just thought I'd bring it up. And so that if you were to plot h, or say its magnitude, and if h were real or complex, you would find that it would be periodic in 2 pi. If h of omega, if h of e to the j omega, I'm sorry, if little h of n, if the impulse response were complex, then you wouldn't necessarily have symmetry around omega equals 0. But whatever, you would definitely have periodicity over 2 pi. You always would. Whether it's complex, conjugate, symmetric, or not. You always have periodicity over from omega to omega plus 2 pi. 2 pi periodicity, you always get that. All right.
So, no matter what the XMN is, the frequency response is always periodic.
Yes, that is correct.
So
That is.
even if the input XMN is periodic or not periodic, the frequency response is periodic.
That's correct. That is correct.
And the frequency response is continuous,
Right.
even though the input is discrete.
That's right. You had this class? No, that's right. No, because, yeah, I mean, there are several different cases that people look at. One is x of n is discrete but periodic, in which case, if the input's periodic, then the frequency response will be discrete, actually. It'll be periodic, of course, but it will be discrete. If, on the other hand, x of n is not periodic, then x of e to the j omega is continuous, but it's still periodic. So, yeah, you're right. Didn't have this before. Anyway, what do you think? No. Okay, so let me go to what I think is some boring stuff, but for completeness sake, I will cover it because it's not clear that you've seen or been exposed to the discrete-time Fourier transform. You will learn in DSP, to become true DSPers, you will learn that the name of the game is acronyms. And so in continuous systems, there's just one thing called Fourier transform for continuous systems. And you remember if you took 301 or... That's kind of weird. Did something happen? Oh. Anyway, if you've had 301 or the prerequisite for this, you've undoubtedly seen continuous Fourier transforms. So there's just one continuous Fourier transform, namely the continuous Fourier transform. But in the discrete world, there's a lot of different, well, there's not a lot, but there's a couple of different variations or varieties of Fourier transforms, discrete Fourier transforms. And one is called the discrete-time Fourier transform, the DTFT, which is what I'll talk about here. That's what I mentioned before, alluded to before. Namely, the definition of the discrete-time Fourier transform is simply this, as I've written before, okay? Later on in the class, there's something else in DSP called the discrete Fourier transform without the T. It's just DFT. That means something totally different. That's related to the DTFT, but it's something totally different for finite sequences. And then there's ways of implementing it called the fast Fourier transforms. All these different FFT, DFT, DTFT, all these different acronyms. They'll drive you crazy, but we'll go through them one at a time. Okay, so but the discrete-time Fourier transform is defined as this. And we saw that pop up when we looked at the responsible linear time invariant system to a complex sine wave. We obtained the result of the response in terms of the DTFT of the impulse response, x. But this is just the general DTFT. And actually from this, what the gentleman was saying was correct, which I may come back to later, is that if x of n were periodic, then you would find that x of e to the j omega would be discrete function of omega. Well, I'll show you an example of that, as a matter of fact. Anyway, that is the discrete-time Fourier transform. If you were to plot x of e to the j omega squared, magnitude squared, that would kind of tell you how the energy in the discrete time signal x of n is distributed in frequency, see? So that's the main usage of the discrete time Fourier transform. It tells you how the input signal, which is in the time domain, it tells you its frequency content. Usually, not always, but usually we plot magnitude of x squared in dB, as I mentioned earlier when I talked about the magnitude of h. So in fact, if you wanted to convert the magnitude squared of x, of e to the j omega, into dB, it would be 10 log to the base 10 of the magnitude of x squared, which is also equivalent to 20 log to the base 10 of the magnitude of x without the square. And that's what I had before. But obviously those are equivalent. So here are some simple examples of the DTFT with some simple sequences. What about our friend the impulse response? That's pretty simple. For the impulse response, x of e to the j omega is 1 for all frequency omega. X of e to the j omega is 1. So what that's saying is that when in time my input is focused at one particular time sample, it could be multiple time samples, but basically when my input is focused in time, then in the frequency domain it'll be spread out. The energy will be spread out to all the different frequencies. Okay? So in this case, in time, all the energy is focused at n equals 0 for this example. But in frequency, the magnitude of x is spread out for all frequency uniformly. Example 2, the complex sine wave. Now, in this case, and notice also in response that x of e to the j omega is continuous. It's just a constant. Now, let's take example 2. Here's a case.
That's why the impulse is the most broadband signal.
Right. It is. Because I say that because, well, it's like in the continuous world. It's just constant frequency for all frequencies minus, in this case, minus pi. Everything's periodic. But that's it. That's the most broadest band signal. Now I'll take an opposite example, the complex sine wave. Now the complex sine wave is periodic in the time domain. In fact, in time, its energy is spread evenly. If I were to, x of n is e to the j omega naught n, the complex magnitude of x of n is 1. So there's energy the same everywhere. But what that suggests is, therefore, in the frequency domain, the energy is going to be discrete in discrete frequencies. And sure enough, it is, even though I have to say this is a case where the DTFT, strictly speaking, doesn't exist, but it does if you use these generalized functions. And by generalized functions, I mean the Dirac delta function, okay? Not our impulse response delta. That's a finite delta, or what they call Kronecker delta function. Now I'm talking here about the Dirac delta function. And the Dirac delta, well, here it is. So if, in fact, x of n is periodic, in this case e to the j omega naught n, then look at this. Then the DTFT of that is actually can be expressed in terms of these Dirac delta functions. So here is what they look like. I just sketched out some. First of all, the Dirac delta function has two properties, two important properties, unlike the Kronecker, the discrete delta function. First of all, it really blows up at x equals 0. Delta sub d, I'm calling it delta sub d to distinguish it from our delta. It does blow up at x equals 0, goes to infinity, but if x is not 0, it's 0. And it also has the property, it's a continuous function, but I mean, I guess they call it a generalized function. If you integrate it, it has the property that it integrates to 1. So you can think of the Dirac delta function as a sequence of functions, each with constant unit area, but they keep going to infinity. Thus, x of e to the j omega is a periodic pulse train. So that's what it would actually look like. These are the values of x. And you can see that if you take a sine wave and do a very large Fourier transform, you can take your computer, we'll show examples later on where you can do that in MATLAB, for example. Yeah, you will find that the the DTFT of the result will just be, it'll be all zero, except at the frequency of the sine wave, it'll be this infinite spike. And then that'll repeat, of course, period 2 pi. So within the interval from minus pi to pi, though, you will just get one spike, and then that repeats every 2 pi. So for minus pi less than omega less than pi, you just find this. So periodic input sequence, discrete, it's a perfect example of what you were saying. Discrete Fourier transform, discretely, not continuous, but it is still periodic. So it's always periodic. Thus, in frequency, energy is focused at omega equal omega naught. And yeah, notice the duality of the previous example. Wow, I thought I'd finish this. Right-sided geometric sequence. I mentioned that at the very first class. And it's of this form. X of n equals, it's our impulse response, friend of that first order difference equation, by the by, u of n, okay? And I will assume, I guess I will assume that the magnitude of alpha in this case is less than 1. In fact, I have to assume that, or the DTFT doesn't exist. And the DTFT is obtained from the geometric sum formula. So the DTFT looks like this, right? Equals summation n equals 0 to infinity, because it's right-sided starting at n equals 0, alpha to the n times e to the minus j omega n. But if I'm clever, I can notice that this whole thing I will write as t to the n, where t is equal to alpha times e to the minus j omega. So I can apply, as long as alpha is less than 1, I can apply the geometric sum formula, which is this. Summation n equals 0 to L minus 1 t to the n is this, and as L goes to infinity, and as long as t is less than 1, then this just goes to 1 over 1 minus t as L goes to infinity. So that is this is a perfect time to use the geometric sum formula to compute this discrete-time Fourier transform, and when you do that, you get this result for the DTFT of this geometric sequence. And I wrote it like this, using the geometric sum formula, and then I plot it, or I actually compute the magnitude squared of x, and I get this function. And if I were to plot that, then look what I get. I get something which has more energy at omega equals 0 than at omega equal plus or minus pi. And then again, outside of this, it just repeats. So I'm getting something in the frequency. So this says that the geometric sequence, alpha to the n u of n, has a Fourier transform that looks like this. So what it's saying is that if I look in the frequency domain, remember the discrete-time Fourier transform tells you how the time impulse, or the time input sequence, is energy spread out in frequency. It says that it has more energy at omega equals 0 than it does at the higher frequencies. So this would say that, so in the frequency domain, most of the energy, more of it, I should say, is concentrated at omega equals 0, corresponding to what we call a low-pass spectrum. Low pass just meaning that most of the energy at the low frequency passes through, or is present. But now this does depend on alpha too, because if alpha were 1, this would be infinity. If alpha were 2, it would be some value. But if alpha were negative, it'd be a whole different picture. What happens if alpha is real but negative, still with the magnitude of alpha less than 1? Then we would get, we still have this result, but if we plotted that, what we would find is that we'd get a spectrum that looked like this in shape. So now most of the energy, instead of being at the lowest frequency, it's actually at the highest frequency. Is at the highest frequency, omega equal pi, while there's little energy at omega, or much less energy at omega equals 0, and we call that a high-pass spectrum. So what is going on? Well, again, keep in mind, x of n is equal to alpha to the n times u of n. Now, when alpha is, so if I were to plot this, that's a good way to see it, x versus n, I would find that if alpha is greater than 0, you get something like this, and it's less than 1 magnitude, okay? That would be alpha greater than 0. But what happens if alpha is less than 0? See? X alpha is less than 0. Then what's going to happen is when n is 0, you're still going to get some value here, no problem. But when n is 1, you're going to get this thing flipped. And then you're going to get it flipped like this and flipped like this. So it's going to be like an alternating sequence of decreasing value. That rapid variation in the samples, where it's going plus, minus, that actually produces more energy at the higher frequencies out here. So depending on the sign of alpha, you either have a low-pass spectrum or a high-pass type spectrum for a geometric sequence. What happens if alpha goes to 0? Well, in that case, x of n, as you can see, would have to go to a delta, a Kronecker delta function, okay, because except for n equals 0, as alpha goes to 0, this goes to 0, and x of e to the j omega goes to 1, which you could also see by looking at this, the formula here. I'm not going to be able to finish this stuff. Oh, well, it's all right. By using the DTFT, a very important question arises. Given the DTFT, x of e to the j omega, can I go backwards? Can I recover x of n? If it's a good transform, you should be able to, and the answer is you can. The answer is yes, and it's true because of the orthogonality of the complex sine waves. Namely, this is what I mean by the orthogonality. And because of that, then if you what you would do is you write x of e to the j omega as equal to, oh, never mind, I'm repeating myself. Anyway, because of the orthogonality of the complex sine waves, and by that I mean that the integral from minus pi to pi of e to the j omega n minus m is going to be 0 unless m is equal to n. If you normalize that integral by 2 pi, then in fact it's a Kronecker delta function. And so there, if given that property, now you can prove that, yes, you can recover x of n. Now consider this integral 1 over 2 pi minus pi to pi e to the j omega k x of e to the j omega, and you will find that, lo and behold, that's equal to x of k. So that's the inverse DTFT. This is the inverse IDTFT. So you can go either way. X of n, go to x of e to the j omega, x of e to the j omega, go back to x of n, as you wish. Either way. So the answer is yes, we can always recover x of n using the inverse DTFT. Now, one thing I do want to point out, and I'll come back to this because it's a very interesting point. X of e to the j omega, once again for the 10th millionth time, e to the minus j omega n. What I want to point out, this does not exist for all n. For all x of n. Does not exist for all x of n. I mean, what if, example, x of n, let's say that was equal to 2 to the n times u of n. As a silly example, clearly we can't sum this up. It diverges, okay? So I just want to make that point right now, kind of get it in your minds, and we'll come back to it when we talk about the Z transform. But in any case, this is the inverse Z transform, and it's defined. It's typically defined as an integral only from minus pi to pi, because everything's periodic outside of that. And that's one reason, wherever it was, if I still have it. Do I have it? Oh, yeah. And that's one reason, or that's an important reason why the only physically meaningful part of x of e to the j omega is defined over this interval, minus pi to pi, like I drew here. Okay. Now, to really understand that, we have to talk about sampling, which I'll talk about later on, actually in the second half. Or, well, I don't know, but later on. So that is the inverse DTFT. As an example, I go back to the complex sine wave, and I wrote the DTFT of that as the sum of these discrete lines, periodic in 2 pi. And if I do the inverse DTFT of that, I will get, in fact, x e to the j omega naught n, because I'm restricting the integrand from minus pi to pi, which proves that e to the j omega naught n and this guy are DTFT pairs. So that is that. And oh yeah, now let's return to our linear shift-invariant system. All right, let me see what I can say about that. Let's return to our linear shift-invariant system. Y of n equals h convolved with x, and we will compute the DTFT. So here is our system. Y of n is, this is LTI, summation k, h of k, times x of n minus k. Now what I'm going to do is compute y of e to the j omega from its definition. So here is, and I've done it right here for you, y of e to the j omega is the DTFT of y of n. Now what I will do is substitute for y of n this, and I end up with this really a double sum, and it's a sum over the time index, and it's a sum over this k, the convolution index. And what I will do is move that convolution index sum out, because k doesn't depend on the time. And so I will move that out. I will move the h of k out along with that sum over k. And then I will consider the inner sum, which is over n, x of n minus k times e to the minus j omega n. And if we take a look at this, we can relate this to x of e to the j omega, the DTFT of x of n, by a simple change of index, some index. If we substitute, like some other index, let's call L, and let L be equal to this, n minus k, or equivalently, n is equal to L plus k, then this term here you can see is equal to this, equal to this. Lo and behold, it's equal to, it can be related to x of e to the j omega by this introduction of this phase factor. So what this is saying is that x of n minus k has a DTFT of e to the minus j omega k times x of e to the j omega. So if you know the DTFT of x of n, you know what it is for x of n minus k. And we end up with this, and we end up with this result, that the DTFT, this guy of y of n, can be written as, and this is the big one, h of e to the j omega, which is the Fourier transform, the discrete time Fourier transform of the impulse response, times the DTFT of the input. So with a linear system, linear time invariant system, LTI, we have two now important results. One, y of n can be written as convolution of the impulse response with the input, or, that's in the time domain, or in the frequency domain, y of e to the j omega can be written as the product of the DTFT of the impulse response times the DTFT of the input. And maybe not clear now, but it will become clear in just a little bit, actually, and you will see why in dealing with these difference equations, which involve these time shifts, if you can transform them somehow into the frequency domain, they're much easier to deal with and to solve. So we'll come back to that later. Anyway, this is the fundamental theorem for linear shift-invariant systems. Namely that for a linear shift-invariant system, the DTFT of the output of the system can be written always as the DTFT of the impulse response times the DTFT of the input. So convolution in the time domain is equivalent to multiplication in the frequency domain, and the reverse is also true, as we will use later on. What do you think now? I know the class supposed to end at 9:10. Shall we? Let's make a night of it. No, I got to get out of here or else I'll fall asleep. But anyway, so we'll cut it a little bit short this time, but that's all right. And we'll end there. I will continue next time. I thought really I could finish this, but anyway, I'm almost there. And then next time your homework is due. So look, again, if you have any questions about the homework, before you've turned it in, I mean, like you're trying to do the homework and you have questions, the best is to send me an email. And I tell you, we can clarify everything and clear it up. Also, if you're finding, geez, you know, I've run out of time, send me an email before you run out of time. And when you do that, let me know, hey, can you give me till, you know, the end of the weekend or something. Just give me a time period. And no request is ever denied. And that's the beauty of the class. Okay, guys, I will see you next week. Thanks for attending.